Great. Yeah, thanks for having me. I'm very excited to be sharing this research with you all. So this is the research I did for my master's thesis with my supervisor, Felipe Rincon. And yeah, so if you have any questions during the talk, just please feel free to interrupt me. We're going to have plenty of time to get through the slides, or at least what I want to get through. And if I have extra time, there'll be a little bit of extra content that I can share with you. Great. So I want to make it sort of very explicit what I'm going to talk about, just to give you all a roadmap. So I'm going to start by giving a lot of background. So I'm hoping that there will be at least 30 minutes worth of background so no one gets lost when we start talking about the results. And then I'll tell you what the sort of titular object is, paving tropical ideals, of the sort of elementary results that allow us to work with paving tropical ideals. And then I'm going to tell you sort of the most important thing that we get out of this paper, which is about examples of paving tropical ideals and how we can use them to prove useful results. So that's the structure of this talk. And so I want to motivate what I'm doing before I even get into the background. So I know a lot of you have an algebraic geometry background, but you might not know much about tropical geometry or about combinatorics. So I'm going to start by telling you about tropical geometry. So tropical geometry is a tool that algebraic geometers can use, and it essentially opens up the toolkit of combinatorics to the study of algebraic geometry. And so how do we do this? So the object, the main object, or one of the main objects we study in tropical geometry is called the tropical semiring, which is this set R bar, which is the set of real numbers together with infinity. And it has different operations than we're used to. So A tropical plus B is the minimum of A and B. And A tropical times B is just the standard sum of A and B. And so the tropical semiring. And so a lot of tropical geometry takes place here, but we're actually going to be more considered with a subring of the tropical semiring in this talk called the Boolean semiring, B. And it's just going to be 0 and infinity. So 0 is like, it's the multiplicative identity element, and infinity is the additive identity element. And this is the Boolean semiring. All right, so this is where tropical geometry is taking place. And this is a tool in algebraic geometry. And so how do you go from algebraic geometry to tropical geometry? Well, if you have a field K, we can consider something called a non-Archimedean field valuation, which is a map that takes you from K to the tropical numbers T. Oh, I called it T here. It should be R bar. Yes, so I'm not going to tell you what a non-Archimedean field valuation is because it's not very important to this talk. I'm going to tell you an example of a non-Archimedean field valuation, though, and it's the trivial valuation. So the valuation we're concerned with in this talk is called the trivial valuation, and it says that if you give me an element A of K, then I'm going to send it to 0 if A is not the 0 element of K. And if you give me the 0 element of K, then its valuation is going to be infinity, which is the 0 element of the tropical semiring. So it's a really simple valuation, and this is the only thing we're going to be concerned with, which is why I'm not defining valuations in general. And so this might seem kind of restricting, especially since if you know some tropical geometry, you know that the trivial valuation is kind of like a not so nice valuation in general. But it turns out that many properties of tropical ideals, which is sort of the objects we're working with, can actually be reduced to taking zero-dimensional ideals and reducing the valuation to be trivial. So this is why this is sort of an appropriate setting. So this is a bit on how we arrive at tropical geometry. So I want to tell you a bit about the research I'm doing inside of tropical geometry, and it's called tropical commutative algebra. So I like to start with this diagram. So up top, we have the setting of algebraic geometry where you have ideals and varieties. But on the bottom, we have tropical geometry, and we have maps that take us from the land of algebraic up to the land of tropical geometry on the bottom. And so this has to do with extending this valuation we just talked about to work in the setting of ideals and varieties. And so how do we do that? So over here on the left, we have an ideal in a polynomial ring over K. And so the coefficients of my polynomial, C sub u, are living in K. And so what I might think to do with my valuation to end up, with something tropical is I can just, take the valuations of my coefficients. So I send this polynomial in a polynomial ring over K to a polynomial ring, or a polynomial in the polynomial semiring over the tropical semiring. And so that's how we work with polynomials. We just coefficient-wise apply our valuation. And then on the right-hand side, we have our variety. And this is just sitting in K to the n. So I just have, n coordinates, and each coordinate lives in K. And so what I might think to do is, well, I can just apply my valuation coordinate-wise. And so these are my two maps, and this is how we descend from algebraic geometry to tropical geometry. And so, one of the important questions here is, why do we do this? Why is this a good idea? Well, algebraic geometry studies the relationships between I and the variety of I, and tropical geometry can study the trop of I, the tropical ideal of I, and trop of V of I. And there's some, variety relationship between trop of I and trop V of I. And so it turns out that tropical geometry works because this diagram commutes. So the notion of taking variety in tropical geometry, I'm not going to get into it because it's a bit complicated and it's not so important to the rest of the talk. It's compatible with, our understanding of algebraic geometry. And so why would we want to do this in the first place? So there's a very good reason. It's not just that this diagram commutes that we might want to do this. The tropical geometry has some very, has a very useful property. And it turns out that, tropical varieties, trop V of I, are very special objects. They're not just, something sitting in space. We don't know what the structure is. They actually have a lot of combinatorial structure to them. So trop V of I, so if you give me an ideal, you take its variety, and then you tropicalize it, this is going to be a polyhedral complex. So, I'm not just getting something weird in space. I'm getting a collection of shapes that intersect very nicely. And there's only finitely many of these shapes. So I sort of have a finite amount of data being presented. And it's it has a sort of nice balancing condition on the top dimensional polyhedra. So it's a very robust combinatorial structure that we're working with. And this sort of this opens up a lot of combinatorial techniques to allow us to study trop V of I and therefore V of I. So what we're working with in tropical commutative algebra is sort of, the question of, what goes over in this bottom left-hand corner with trop of I. So trop of I is going to be an ideal in a polynomial ring over the tropical numbers. But it's not just any ideal. Like if I just take any ideal in the tropical, I'm just going to call it a tropical semiring, then I'm not going to end up with a finite balanced polyhedral complex as my variety. There's something very special about the structure of my ideal I that gives me this structure. And so we're concerned with what goes over, what needs to go in this corner in order to ensure that I get these nice combinatorial properties. And it turns out that we do have a very good candidate for what should go here, and it's these things we call tropical ideals. So before I tell you what a tropical ideal is informally, I'm going to tell you what about the ideal I gives it this structure. It turns out that it's the variety of I, when we tropicalize it, becomes a finite balanced polyhedral complex because I is a linear space. So the linearity of I seems to be what gives me this nice combinatorial structure when I tropicalize. And so what we do for tropical ideals, so if you think about it, minimum, the minimum A and B, so tropical addition, has no inverse. So there is no subtraction. And so we don't really have linear spaces in the traditional sense. We don't have, a way of working with linear spaces. So we need to work with something more general than a linear space. And fortunately, combinatorics has an entire sort of subfield dedicated to generalizing the idea of linear independence and dependence, and this is called matroid theory. So what we do for ideal, so a tropical ideal is an ideal over the tropical semiring. It's a polynomial ideal over the tropical semiring. That's also a matroid, so it's a generalized linear space. And it turns out that with this, assumption, we do end up getting varieties that are finite balance polyhedral complexes, as well as a lot of other more useful tools. And I'll tell you more about those later. So that was sort of motivating tropical geometry and commutative algebra. So now I want to tell you about the motivations for this paper in particular. So for paving tropical ideals. So it turns out, so before I get to this, so a very reasonable question we might ask is the map that takes ideals to tropical ideals, is it a surjective map? Are all tropical ideals of the form trop I, where I is some ideal living in a polynomial ring over a field K? And it turns out the answer is no, which is, I suppose, good, because now we're working with something that's indeed more general. So there's a caveat, and it turns out, so we'll say a tropical ideal is realizable if I can find an ideal I over a field K, and I can tropicalize that to obtain my tropical ideal. And otherwise, we're going to say a tropical ideal is non-realizable. And it turns out that non-realizable tropical ideals are very hard to construct. We don't have a lot of intuition about how to construct them, and this is a problem. Another thing that we're interested in for this paper is that Maclagan Zajaczkowska in her PhD thesis showed in 2018 that if I'm looking at zero-dimensional degree 2 homogeneous tropical ideals in n variables, then there's a one-to-one correspondence between these ideals in sublattices Z. So there's something really nice about these tropical ideals that gives them this nice sublattice correspondence. And so these are the two things that motivate this paper. Tropical ideals are hard to construct, and there's some beautiful correspondences between sublat, so some group theory or something going on here. And so these are our motivations. So what do we do in this paper? So we provide a very simple way of constructing zero-dimensional tropical ideals in any degree. So this is going to be very useful because, before, constructing an example of a non-realizable tropical ideal was very hard. And now we have a way of sort of trivially constructing them, at least in 0 dimensions. And so the other thing we do is we understand how the degree 2 sublattice correspondence established by Zajaczkowska generalizes combinatorially into higher degrees. And so those are the two things I'm going to sort of outline. And so how am I going to go about doing this? So first, we're going to identify a subclass of tropical ideals that admits a well-defined notion of ideal generation. And this is going to be the idea behind paving tropical ideals. Then we're going to study the condition. So if I have an idea, like if I have a notion of ideal generation, one thing we're going to need to do is study sort of the conditions on my generating set that controls the structure of my ideal. So we're actually going to be able to determine like a nice way of generating these things so we can control the output of our generating process. And then finally, we're going to use these conditions we construct to actually construct and study examples. So that's the outline, the specific outline of this talk. Great. So thank you for sitting through 15 minutes of motivation. So now I'm going to get into the background. So the most important thing we're going to need to talk about is matroids, because these are the things that are making what tropical ideals stand out from just regular ideals in the semiring. And so the most important way to define a matroid for us, as there's many definitions, is through the circuits of a matroid. So a matroid presented by circuits, it's a set E along with a collection of subsets of E that we're going to call circuits. So this script C is the set of circuits. And so our circuits need to satisfy 4 conditions. So first off, the empty set is not a circuit. The second condition says that all of my circuits are finite. The third condition is that my circuits are incomparable. So if 2 circuits, C1 and C2, are such that C1 is contained in C2, then C1 has to be equal to C2. So they're all minimal elements in my collection. And so the non-trivial axiom for circuits is called the circuit elimination axiom. And this is sort of a generalized idea of subtraction that can be done without any attached or any rings. So this is sort of formally, if you give me 2 circuits, C1 and C2, and say that C1 and C2 have an element E in common, then I can find a third circuit that lives on the union of C1 and C2, but doesn't contain E. So I've found a way to subtract E between C1 and C2. I can eliminate it and get a new circuit, C3. So this is how matroids are generalizing linear dependence. They do it by generalizing subtraction. And so this is going to be why things work out nicely for tropical ideals. But before moving on from the definition of matroid, I need to say a few more things just for a bit of cohesion. So the sets of E that don't contain a circuit are called independent, because circuits are also known by another name, which is minimal dependent sets. So the things that don't contain a minimal dependent set are independent. All right, and we're not going to be working with independent sets, but we do need them for this more important definition, which says that if I look at my collection of independent sets, and I look at the size of a maximal independent set, this is going to be finite in our case. We're going to call this number the rank of the matroid. The size of a maximal independent set is the rank of our matroid. And this is directly generalizing matrix rank. So if you gave me what would be called like a representable matroid, so a collection of vectors in space, I can put those into a matrix and compute the matrix rank. And this is sort of exactly what we're capturing here with matroids. Great. So I want to go over an example. It's my favorite example. So this is how we might traditionally think about linear independence and dependence. So we start with some points in space. So many of us know that if you have 2 points, you can define a line. And if you have 3 points on a line, there's sort of a way to add these vectors together to end up getting 0. So there are 3 points on a line is a redundant amount of information. So it's a dependent set, or in this case, it's going to be a circuit. So 3 points on a line should be a circuit in this picture. And also, if I take 4 points in a plane where there's no lines, so there's no 3 of those points on a line with each other, this is a minimal dependent set. So it's also a circuit. So I'm going to start with these 2 dependent sets, these 2 lines with 3 points each, sitting in space, and I'm going to draw some more lines between them. So I'm basically connecting the capital letters to the lowercase letters that are different from them. And I get some intersection points, and I'm going to label them 1, 2, and 3. And so it turns out if I collect my circuits as I just described, so 3 points on a line, 4 points on a plane that don't contain a line, then this gives me the circuits of a matroid. But if you look at this picture for any amount of time, you'll probably realize that 1, 2, and 3 are clearly on a line with each other. So if I'm actually drawing this picture in space, then 1, 2, and 3 are also on a line. And so this is actually a very old theorem in geometry called Pappus's hexagon theorem. And it says that if I drew this picture in any vector space, then 1, 2, and 3 must lie on a line. And so this gives me a matroid. So this gives me the real matroid. So if I were actually drawing this picture, this is the matroid I'm trying to draw. we already said that, this previous picture when 1, 2, and 3 weren't on a line is also a matroid. But this sort of contradicts Pappus's hexagon theorem in that 1, 2, and 3 must have been on a line if I was drawing this in space. So this sort of is saying that not all matroids come from vectors in a vector space. They're more general than linear spaces, which is what makes them such a powerful tool. Great. So that was the first example I wanted to go over. So not all matroids come from linear spaces, and similarly, not all tropical ideals come from ideals. So the second the most important example of a matroid for this talk is going to be polynomials in an ideal. So if you give me an ideal, it's a linear space. And so I can pull a matroid out of this. So how am I going to do it? So I want to pull just the circuits out of my ideal. So I want to look at what I would call the support of a circuit. And so how do I find what is the support of a circuit? So I'm going to look at this map. So let's say, this polynomial I've got here is an element of my ideal. I'm going to look at the exponents u. And so the exponents are vectors in z to the n. And I only want to collect the ones where the coefficient cu is not 0. So the ones that actually show up in my polynomial. And this set is going to be called the support of my polynomial. And so what I want to do to get my circuits for my matroid is I just want to take the minimum ones, right? Because I need a clutter. So I look at my ideal and I look at the polynomial with sort of the smallest sets of exponents possible. And these are going to be these sets of exponents are going to be my circuits. And so formally, an ideal gives us a matroid on the set z to the n. And this is going to be what we call the underlying matroid of my ideal. And so this is what we're going to be working with through most of the talk. So are there any questions so far? All right, so I'll keep going. Great, so with these definitions, I think we're ready to formally define a tropical ideal. So a tropical ideal in a polynomial semiring over the tropical numbers, it's just an ideal whose polynomials of minimal support form the circuits of a matroid. So they have some generalized notion of subtraction between them. And so it turns out that this definition has great consequences. But before I tell you about the great consequences, I'm going to tell you about the not so great consequences. And so tropical ideals aren't very nice for some reasons. So let's start with an example of a realizable tropical ideal. So ideal I, it's a principal ideal generated by x minus y in the complex numbers, or in a complex polynomial ring with two variables, right? So this should be a reasonably nice ideal, and maybe we expect its tropical ideal to be reasonably nice. So let's consider trop of I to sit in the tropical polynomial semiring with two variables. And it's not going to be finitely generated. And so why isn't it going to be finitely generated? And it turns out just, I have these binomials in I of the form x minus y to the d. So I multiply x minus y by some cyclotomic polynomials to get nice cancellation, and I get x to the d minus y to the d. And so when I tropicalize I, I'm sort of tropicalizing every polynomial. So I'm replacing the coefficients all with, tropical 1, which is 0. And I just end up getting x to the d plus y to the d. So this is going to be in my tropical ideal. So why isn't this finitely generated? There's no cancellation. So if I'm trying to generate my binomials, I have, x to the d plus y to the d for every d. If I took any finite collection of these things, like if I multiply by a monomial, I'm not going to end up with something of the form x to the d plus y to the d. But if I multiply by a binomial or something with more terms, I'm going to end up with something that has more than 2 terms because there's no cancellation. So there's no finite collection of these things that I could take to generate all of the other binomials in this ideal. So this thing's not finitely generated, but it's not even clear to me that, maybe I just say, well, is it even generated by all of the x to the d plus y to the d? And that's not even clear to me, because since this thing locally a matroid everywhere, you sort of have to specify how subtraction works everywhere. So between every pair of polynomials, you have to have subtraction defined for you, and we're not sure. This is what's not so nice about tropical ideals, is that matroids can't be generated so trivially, and so tropical ideals can't be generated so trivially. But there's actually a lot of reasons to like tropical ideals. So why are they nice? Here's just 4 reasons. So the variety is going to be a finite balanced polyhedral complex, as before. Tropical ideals satisfy the ascending chain condition, so I can't just construct larger and larger tropical ideals. Eventually, I have to become trivial, or like the whole polynomial ring at some point, in an infinite number of steps. Tropical ideals have a well-defined, like, Hilbert polynomial. It's not a function, it's an actual polynomial. And this is actually going to encode meaningful combinatorial data about our ideal. And they also satisfy the weak null-Snellen stats, and it's not on this list, but they're compatible with existing ideas of tropical scheme theory. So they're very nice objects, theoretically. They're just hard to work with in practice. So one more notion we're going to need. So we know what a tropical ideal is, but we need the sort of paving part of paving tropical ideals. So we're going to need this definition. So a paving matroid of rank R is a matroid of rank R whose circuits have size R or R plus 1. So R plus 1, if my rank is R plus 1 is the maximum size a circuit could possibly have. And so I'm sort of allowing just a very small amount of deviation in the size of the circuits. You either have the size exactly the rank of the matroid, or as a circuit could possibly have. And it turns out that just by restricting to this case, you actually get a lot more structure on your matroids. So matroids generally are very complicated to work with, but paving matroids are very nice to work with. And so before I go on, I do want to say that this is sort of a reasonable class to look at, conjecturally at least, because it's been long conjectured that paving matroids are asymptotically most matroids. So if you pick a random matroid that's of, with 1 million elements, then, asymptotically you're most likely to pick a paving matroid. And this is a long-standing conjecture, and there is evidence to suggest it's true, but it's not proven yet. So this is why we thought this was a reasonable class to work with. And so an example of a paving matroid is exactly what I showed you before. So these so-called Pappus and non-Pappus matroids are both examples of paving matroids, because if you think about the way we define them, this thing has rank 3 because it's sitting in a projective plane, so the dimension is actually 3. And my circuits were subsets of size 3 and subsets of size 4. So this is a paving matroid. Great. So it turns out that circuits aren't the best way to work with paving matroids, because for general matroids, that's what we have. But for paving matroids, we can do better. And this is because the circuits of paving matroids sort of have aggregate behavior. So if circuits share enough terms in common, they have to behave very similarly with their circuit eliminations. But this isn't exactly obvious from this definition. So we're going to work with a slightly different definition that turns out to be equivalent for paving matroids. And it's going to capture this collective behavior very nicely. So what we're going to work with is something called generalized partitions. And so this is sort of like a partition of we're not partitioning a set E, we're going to partition the subsets of E of size D for some fixed D in a certain way. So this is why they're called generalized partitions, but I'll call them d-Partitions for the remainder of the talk. So given a set E, a d-partition on E is a set system H, or script H, such that there are at least 2 elements in my d-partition. And for every element of my d-partition H has at least size D. And then sort of the non-trivial part of being a d-partition is that each D subset of E appears in a unique element of my d-partition. So this is the partition part. It says that the D subset appear in a unique block or element of my d-partition. So the elements of my d-partition are going to be called blocks. And so why do we care about these things? It turns out that d-partitions exactly encode paving matroids of rank d+1. So these are equivalent definitions. This is what makes paving matroids very nice. And so what we're going to need to be able to do, I'm not going to tell you how to go from the circuits of a paving matroid to a d-partition. What's going to be more important is knowing how to go from a d-partition to the circuits. So the circuits, if you give me a d-partition, it has sets of size d, and it has sets of size d+1 and greater, right? And so what I want to do is I want to look at the sets of size d+1 and greater, and I'm going to look at, I'm just going to take if I have a block of size at least d+1, I can take all of its d+1 subsets, and that's my circuits of size d+1. So I just go block by block, I take all of the subsets of each block of size d+1, and those give me my circuits of my paving matroid of size d+1. But I also need some circuits of size d+2. It turns out these are sort of implicit from the ones of size d+1 because I can sort of just fill them in because d+2 is the maximal size of the circuit. So I just take all the d+2 subsets of my set E that don't already contain a circuit of size d+1. And this is how I can construct my matroid. Yes, and I'm not going to tell you how to go the other way, but if you were to try and aggregate your circuits into blocks, it would tell you that, the circuits that join together into a block have very similar circuit eliminations when it comes to circuits of other blocks. And this is the behavior it's capturing. So we're condensing the information of our matroid into a more useful description. Right. So the most important thing about d-partitions is that we can generate them. We can do it really easily because if you give me a set system on E, and let me just, S has at least size, the elements of S have size d+1 or greater, and the pairwise intersection of its elements are size less than D. So this is like almost a d-partition. Then I can start with forming my d-partition by saying, well, I'm just going to take S, and then I'm going to fill in subsets of size D that aren't contained in an element of S. So d-partitions are very easy to work with because you can generate them in this sort of easy way. And I know we put conditions on S, but we don't have to. There's a canonical way to close a d-partition if it doesn't have these properties. But if we impose these properties, it has nice injectivity properties, but I'm not going to get into that, like when we assign a d-partition to S. So great. So the important thing, so I'm done with the background, and so I want to recap really quick. So the things to take away: ideals are ideals in the Boolean polynomial semirings that are also matroids. Matroids, and thus tropical ideals, are very complicated in general, so they're really hard to work with. However, d-partitions provide us describing the circuits of a paving matroid, and d-partitions can be generated. So we're hoping to use these last 2 points to be able to find a nice way of working with tropical ideals. So here's the titular definition. So a zero-dimensional tropical ideal is going to be called a paving tropical ideal if its underlying matroid is a paving matroid. So pretty simple. Tropical ideals are matroids that are ideals. And so if I want a paving tropical ideal, I just have an ideal that's also a paving matroid. So that's all we're doing here. And so it turns out paving tropical ideals are very nice because d-partitions are very nice. So first off, I'm gonna briefly go over the underlying matroid again in case you want to see it. So if you give me an ideal I can use my ideal I to obtain a matroid, N, called its underlying matroid. And the way I do this is I look at my polynomial, and I look at the exponent vectors in Z to the n for which the coefficient Cu is non-zero. So I'm just taking the exponent vectors that appear, And if I want to get the minimal, these are going to give me, I want to take the minimal such subsets. So I take all of my polynomials, I take all of their supports, and I take the minimum ones. And those are going to be the circuits of my matroid. So I don't just have a matroid on z to the n. This matroid has structure because the ideal I has structure coming from the multiplication map of my polynomial ring. So if I have a polynomial, I can multiply it by a monomial x to the u, and I can sort of translate, my polynomial's exponent. So if I multiply x to the u, if I multiply by x to the u, then my polynomial's exponent vectors, say v, are going to be mapped to v plus u. So in a way, the multiplication by monomials corresponds to translating my exponent vectors by elements of z to the n. And this is sort of descending to my supports because I'm just recording the exponents. So if I'm recording my exponents and I can translate my polynomial, translates the exponents of my polynomial, then the support is being translated. So if you give me an element of my underlying matroid, then the set s plus u, which is the elements t plus u such that t is an s, that's going to be in my underlying matroid for every u in z to the n. So in a very succinct way, the underlying matroid of I is a matroid on z to the n that's also invariant under the z to the n, the action of z to the n. So these have a nice, a very nice structure. They're being acted on by the object that they're sitting in. Great. So we're going to use this to our advantage, that we have this nice z to the n structure or acting on our matroid. And we're going to extend it to d-partitions in particular. So we're going to say that a d-partition of z to the n is z to the n invariant if for every vector u in z to the n and for every block h in my d-partition, the translation h plus u is also a block of my d-partition. And so with this definition in hand, we can really start proving results. So the first theorem we prove in this paper is sort of this natural correspondence that we've just sort of gone over. And that's that if you give me a tropical ideal, then I can tell you with a z to the n invariant matroid on z to the n. I take its underlying matroid, and as we discussed before, the Ront monomials act on this matroid, and that gives me my z to the n action. So there's nothing deep here. And conversely, if you give me the z to the n invariant, a z to the n invariant matroid, I can say, well, here's my circuits. These correspond to some polynomials, and then z to the n invariance is precisely, being closed under the action of my semiring. So there's nothing deep going on here, but the consequences are sort of great in that this implies that there's a one-to-one correspondence between degree d plus 1 paving tropical ideals in n variables and z to the n invariant d-partitions of z to the n. So instead of working with paving tropical ideals, I can just talk about z to the n invariant d-partitions of z to the n, which are a nice combinatorial object. And it turns out we can do a lot with these things. So what we're trying to get at is that we're trying to work with d-partitions, right? We want d-partitions, z to the n invariant d-partitions of z to the n, and we want to be able to generate them because these things are going to be like, infinite things. So we need to be able to generate them. And it turns out that not just any subset of z to the n can be a block in a paving tropical ideal. So if you're trying to construct a z to the n d-partition of z to the n, you can't just say, well, I want this subset S to be in my d-partition. It just doesn't work. And I'll show you an example. So let's try and construct a 2-partition of z squared. All right, so let's start with S. It's these 4 black points. I'm not going to read their coordinates aloud. And so let's say we want S to be a block and in a z squared invariant d-partition of z squared. So the first thing I need to do is I need to be invariant under the action of z squared, right? So if S is a block, then so is S plus 2, 0, these purple dots, right? So S and S plus 2, 0 are both blocks in my D partition, but if you remember what it means to be a two partition, D is 2, my bad. If you remember what it means to be a two partition, it says that every two subset of Z squared is contained in a unique block. But what we're seeing here is that S and S plus 2, 0 overlap in 2 points, right? Their intersection has size 2, and so the set, negative 2, 0 and 0, 0 is not contained, or it wouldn't be contained in a unique block. So S cannot possibly be a block in any two partition of Z squared. That's Z squared invariant. So what can we hope to do? Well, maybe we can try and salvage the situation and produce the smallest block containing S. What's the smallest block containing S? So clearly this has to contain at least S and its translation S plus 2, 0, right? So now we have 6 black points. But now we can sort of realize that we can just repeat this argument infinitely, and we end up getting this infinite collection of points that extends off into infinity in both directions, right? So this is at least the size of our block, but it turns out, now we can play the same game, but do other translations. And it turns out that the minimal block containing S is a sublattice 2Z squared. So this is sitting in Z squared. So I have a sublattice again, just like Zajaczkowska had in her results. So I've ended up at sublattices again, and this isn't an accident. So we're gonna prove a very nice theorem that tells you exactly when blocks can be, exactly when subsets of ZDN can be blocks in a ZDN invariant D partition. So we're going to need a brief definition, which is sort of called, it's d-Sparsity. So we're going to say a subset of ZDN is d-sparse if there's no translation vector in Z to the n that's non-zero. So we're looking at a non-zero translation, such that S intersects its translation S plus U in D or more points. So it's d-sparse if no translation exists, where I get a bad intersection, the intersection that tells me that S can't be a block in a ZDN invariant D partition. Right, and it turns out that with just this definition, we can classify the blocks of a D partition. So let's suppose that P is a ZDN invariant D partition of ZDN. Then any block in S is either d-sparse or a non-trivial affine sublattice of ZDN. And there's no in between. It's one or the other. And so in case you aren't familiar, a non-trivial affine sublattice, it's something of the form V plus L, where V is a translation vector and L is a subgroup of ZDN, right? So this is sort of arriving back at what Zajaczkowska proved in her paper, in that we have some correspondence between tropical ideals that are zero-dimensional and sublattices of Z to the n. Though in her result, it was a one-to-one correspondence. We'll see why we can recover that in the case of tropical ideals. So let's do that now. So if we set D equals 1 and we look at one partitions, and this is for degree 2 tropical ideals, so we're considering partitions because it's saying that every subset of ZDN of size 1 is contained in a unique block, right? So if I'm looking at non-trivial degree 2 tropical ideals, so first off, an important thing to note is that every degree 2 zero-dimensional tropical ideal with Boolean coefficients is a paving tropical ideal. Just because the ranks are so small, you could only ever have circuits of size 2 or 3. If you had a circuit of size 1, then you would be the entire ring, because it's the Laurent polynomial ring. But yes, so everything's a paving tropical ideal when degree is 2. And so if I had any block of size at least 2, then this thing is not one sparse because I can translate it to intersect itself always in one point. So what this means is that, well, I have this block, then it has to, if I have a block of size at least 2, so if I have a non-trivial degree 2 paving tropical ideal, then I immediately recover a lattice for every block that's of size 2 or greater, right? But then I can translate this lattice to sit on any point. So every point in z to the n sits in a translate of this lattice. So this lattice uniquely determines the entire structure of the tropical ideal. And this is why we have a unique correspondence between degree 2 paving tropical ideals and sublattices of z to the n. Very good. And this is precisely what Zajaczkowska proves in her thesis. Very good. So as promised, I'm going to start talking about examples. So don't bother reading this slide. It's mostly just sort of formalism and telling you what I'm going to tell you in a minute. But it's important to know that we can generate, now that we know that either a block is d-sparse or it's a non-trivial affine sublattice, I can generate d-partitions that are z to the n invariant. And so without going into the nitty-gritty of this long definition, I'm just going to tell you the key content. So if you give me a collection of subsets, let's say their size is at least d plus 1, then let's also impose that the translations of my subsets, which are going to end up being blocks, so let's impose that the translation of my blocks intersect in fewer than d points. So they're all d-sparse, and I also want them to sort of be pairwise d-sparse. Then we can generate a paving tropical ideal just by considering z to the n's action on the set system and filling in the d-partition as usual, because d-partitions are very nice like that. So does that make sense? I'm going to close my set system under z to the n's action, and then I'm going to fill in all of the d subsets of z to the n that don't appear within a block that's been translated. So that's all we're going to do. Is that clear? All right. So now I can start talking about our results. So the first result I want to talk about is called lots of paving tropical ideals. That's how I like to call it. And it basically says that, so in degree 2, if we're working with Zajaczkowska's proof or result, it says that, I have a correspondence with sublattices. Every degree 2 paving tropical ideal corresponds to a lattice of z to the n, of which there are countably many. And so there's only countably many degree 2 paving tropical ideals in any number of variables. However, if we just look in one variable, then there's uncountably many degree 3 paving tropical ideals just in this one variable. So there's sort of infinitely more going on here. And it's actually not hard to show this. If we can just construct a family, an uncountable family of such tropical ideals, and it's really, really simple. So proof by example. So let's consider a subset S of the power set. So we're just going to take any subset of the natural numbers. It can be infinite, but it has to have its size at least 3, right? So to this set S, I'm going to associate a new set called T sub S, and I'm basically going to say this is the set of integers 2 to the t, where t is an element of S, right? So I'm sort of, S is just some integers, maybe it's 1, 2, 3, and T sub S is now going to be the set 2, 4, 8. So I'm spacing them apart, and I'm spacing them apart in a very specific way because T sub S is a 2 sparse set. In fact, it's d sparse for every d except 1, as long as t is large enough, or S is large enough. So T sub S is going to be a 2 sparse set. And it's going to be one-to-one correspondence with S, because clearly if you give me T sub S, I can take logarithms and I can give you back S. But if we look at now that, T sub S is too sparse, and clearly it's closed under, if I translate it, it can't, intersect. There's nothing else to intersect with. So this thing can be used just by itself to generate a Z invariant two partition of Z. And this is going to be uniquely determined by T sub S because of this logarithm correspondence. So we can use the same correspondence. So this is very useful because we've just said, now we have sort of this Z invariant two partition of Z uniquely corresponds to the subset S, of which there are uncountably many choices. So if I just go through my uncountably many choices for S, I can construct uncountably many Z invariant two partitions of Z, just like that. And so this is very useful. So this is a nice result. Very good. And so as a corollary, so it was proved earlier this year that most zero-dimensional tropical ideals are not representable. Or we proved that most zero-dimensional tropical ideals are not representable in the sense that if you were to pick a zero-dimensional tropical ideal at random, it's not going to be realizable. And the proof is that earlier this year, Rob Silversmith proves that only countably many zero-dimensional tropical ideals are representable in any degree. So this is a very nice little corollary, so that we might now expect that most tropical ideals are not going to be representable. Very good. So I've got 6 minutes, but I'm not sure if I should stop now to take questions or if I should cover one more result. Do you have an opinion on that, Johannes?
Why don't you just finish your talk?
Yeah, very good. So
if anyone has any questions, I mean, they are always welcome to chip in and ask. But why don't you wrap up and then we open the discussion?
Yeah, so I was going to say some things about another application we do, but yeah, basically paving tropical ideals are very nice because you can glue them together. And we use this, an open question was whether or not a degree 2 paving tropical ideal existed that was representable or not representable. And so the evidence against this is that rank 2 matroids are all realizable. And in one variable, all degree tropical ideals are realizable. But it turns out that we can sort of construct degree 2 paving tropical ideals that are representable, but over a disjoint set of fields. And so we can glue them together and obtain an example of something that's not representable anywhere. And this also opens up new avenues to constructing paving tropical ideals by gluing them together. And there's all sorts of other results in the paper. So thank you for your time. And thanks for listening to me for 55 minutes. Thank you.